Hello. Today I will be presenting work I did along with Dr. Mann and Dr. Luco of the University of Nottingham. So we should start with a very simple question, which is what's inside a black hole? And the interior of a classical black hole is predicted to have a singularity. But the black hole could also have non-trivial topology hidden from external observers by the horizon. And this leads to the question, can an external observer probe the interior topology? And the answer, as you might expect, is yes, with an Unruh-DeWitt detector. And we will gauge the response of the detector with its transition rate. So we'll work with 2+1 dimensional black holes because they are a simpler problem than their 3+1 dimensional counterparts. And specifically, we'll work with the BTZ black hole, which is a quotient of 2+1 dimensional anti-de Sitter spacetime. And other quotients are possible, however, and they give rise to different interior topologies. This is constructed using a discrete group of isometries, which is general for creating quotient spacetimes. So the BTZ black hole can be generalized to form the RP2 geon, named because the identifications switch the singularity from being a singularity to the real projective space. And this is formed by identifying points in the BTZ black hole spacetime. And the object that results is similar to a black hole whose interior is like a Klein bottle. No external observer can perform a classical experiment that will determine whether he is in the BTZ or RP2 geon spacetime. But this changes if he's given a UDW detector. So the major difference between the RP2 geon and the BTZ black hole is that the RP2 geon is not stationary. It does not admit a globally defined time-like killing vector field. And this non-stationary feature is concealed behind the past and future horizons of the black hole. So classically, no external observer will be able to see this dynamical characteristic. But the UDW detector is sensitive to the dynamical character of the geon. Now, a Swedish group has constructed the next simplest non-trivial case for a geon spacetime, and we shall call this the Swedish geon. It has a single asymptotic region like the RP2 geon, but a very different interior. And you can picture its construction by identifying points on the Poincaré disk, which is a representation of anti-de Sitter spacetime. And crucially, there are two generators to the discrete isometry group that produces the Swedish geon spacetime, which complicates matters numerically relative to the RP2 geon, as we shall see. So the transition rate is a functional of the Wightman function, which is the two-point correlator of the scalar field we work with. And we'll obtain the Wightman function of the quotient spacetime from a parent spacetime using the method of images, so an infinite image sum. And the parent spacetime we consider, as you might have guessed, is anti-de Sitter space, which has a known closed form expression for the Wightman function of a massless scalar field. And the transition rate that we will consider is for a detector that's switched on in the distant past and is a function of the readout time, which is to say the moment the detector stops interacting with the field. So the Swedish geon, having two generators in its isometry group, complicates matters. So any combination of the two generators must be included in the image sum. So read out any string of generators, they don't commute, and that will have to be included in the image sum. So Dr. Luco and Dr. Hodgkinson of the University of Nottingham derived the following general expression for Sharp-like switching, when the detector is switched on in the distant past. And usefully, I mean, numerically speaking, it only involves one integral, which is great considering how complicated the integrand is. We can work pragmatically by grouping the terms in the image sum by the number of generators that are acting on x prime. Now, because the generators in the RP2 geon are involutive, there's only 2 image terms. But the Swedish geon has an exponential growth of image terms. The number of image terms with n generators acting on x prime grows as 3 to the power of n. And a finite term approximation is going to be used when evaluating the transition rate because owing to the complexity of the matrix forms of the generators, no closed form expression for the Wightman function can be found, nor even a very clean, nice-looking infinite sum. And we check the validity of our approximation when we include n generators by comparing the transition rate under the approximation with n plus 1 generators. Now, this, luckily, because of the specific matrix form of the generators and the form of the Wightman function in anti-de Sitter spacetime, terms with a large number of generators are suppressed by successive factors of e to the negative square root of m, where m is the mass of the black hole. And we consider only suitably large masses. A very crude reasoning shows that you can find a rough relation between how the mass of the black hole and how many terms you want to include in the image sum. But this is something that's only pragmatic in nature. So in the following, we consider Neumann boundary conditions for the field, but what is to follow is quite general and holds for all 3 possible boundary conditions for the scalar field. And the mass of the black hole is kept the same for all spacetimes. We are considering the anti-de Sitter, BTZ, RP2, and Swedish geon spacetimes. And the UDW detector is external to the horizon and is kept stationary. So, as you can see, the RP2 geon spacetime crosses the preferred spatial slice at t equals 0, and then is constantly different from that of its parent spacetime, which is BTZ. And the Swedish geon, on the other hand, experiences a bump. It approaches what a preferred spatial slice at t equals 0, crosses it, and then dives back down to AdS₃ spacetime. And this is for a gapless detector. So the behavior of the detector in RP2 geon spacetime is as expected. In the distant past, it's not on the preferred spatial slice, which is created from the construction. And as a result, if it's read off in the distant past, our experimenter will be unable to tell whether he or she is in BTZ or RP2 geon spacetime. But as the preferred spatial slice at t equals 0 is crossed, the difference in the transition rate turns on and asymptotes off. And in this way, the UDW detector is a probe of the dynamical features of the black hole interior. But the Swedish geon spacetime is indistinguishable from AdS₃ spacetime in both the distant past and future. So there's a limited window in which our experimenter would be able to differentiate between the 2 spacetimes if he was only using the transition rate to differentiate the 2. So in a nutshell, we can characterize the difference as being a bump versus a plateau. And as I said, the same behavior is observed in all possible boundary conditions. And the modification of the detector to have a non-zero energy gap also does not change this phenomenon meaningfully. As you might expect, all that occurs is that the transition rate acquires an oscillatory behavior, and a smaller mass black hole exhibits the same behavior. This has been checked to thousands of image terms, which, while no means definitive, is very strong numerical evidence that this is a real distinguishing feature of these two geons. So here you can see the same transition rate, but for a gapped a gapped UDW detector. So again, there's an oscillation, but the envelope is a bump versus the rise and plateau. So we found that quantum detectors do probe black hole interiors, and the qualitative difference is due to the different topological identifications made to construct these two spacetimes. And these distinct interiors would be accessible to an external observer, even though the metrics are identical outside of the event horizon. And I'd be happy to take any questions now.